Section 6.4 is going to look at sampling distributions. Up to this point, we have been dealing with populations. When we've been talking about our normal distribution with our continuous variables, we've been looking at the entire population. We've been using mu, which is the population mean, and sigma, which is our population standard deviation. However, we know that we don't always deal with populations. In general, we're going to be taking samples since it is much easier to deal with samples than populations. It's difficult to know everything about a population. So in order to deal with making the transition from dealing with populations to letting samples approximate our populations, we need to discuss sampling distributions. This section is a lot of theory. There's not much actual application. There's not very much problems that we are going to have to go through, but we are going to be learning the background about why we can take information from a sample and apply it to a population and seeing the reason why. The underlying idea here is that we are going to use sample statistics to estimate some population parameters. So let's think about this. If there's 124 students taking ICM or Intro to College Math at Burbank High School this year, how many ways could those students have been selected to fill 4 different classes? Well, we know that there are 124 choose 31 or 1.5834 times 10 to the 29th ways to select 31 students for 4 classes from those 124 students. Essentially, what we are doing is we are taking different samples of 31 from the whole population of 124. There are a whole lot of possible samples that we can take from our population. To accurately represent a sample, we would have to take every single possible sample and see what their outcomes were. Or we have to use the theory that is going to be covered in this section, so that we don't have to then go ahead and take every single sample. And as you can see from this example here, the number of samples possible, even when we have a very small population, is very large. And that's part of the reason why sampling distributions are so important. So what is a sampling distribution? A sampling distribution is the distribution of all of the values of some statistic when all possible samples of the same size n are taken from that sample population. Essentially, if we took all possible samples of some size and then we found some statistic, that statistic could be the mean, the proportion, the standard deviation, the variance, and then we organized all of those results into a table, we would have a sampling distribution. Some notes here: the sampling distribution of the mean targets the value of the population mean and tends to be normally distributed. The sampling distribution of the variance targets the value of the population variance and tends to have a skewed right distribution. And the sampling distribution of the proportion targets the value of the population proportion and tends to be normally distributed. We are going to see this throughout what we are talking about in these notes and then in the future, in the next section. Unbiased estimators. An unbiased estimator is a statistic that targets the value of the population parameter. Some examples are the mean, the variance, and the proportion. Biased estimators are statistics that do not target the value of the population proportion. Essentially, unbiased estimators we can use to make inferences about our population from a sample. But biased estimators do not allow us to make inferences about a population from a sample without doing an extra step or without changing something. And then remember that the standard normal distribution, we talked about this in the last few sections, a normal probability distribution that has a mean of 0 and a standard deviation of 1, and the area under its density curve is going to be equal to 1. This section is important because of the fact that it allows us to take a sample from a population, collect data from that representative sample, and then make an inference about the population. Without the concepts in this section, we would have to go through and take every single possible sample, which would take a long time, and it would be very tedious. What is a parameter? What is a statistic? And how is one related to the other? We usually use P to represent population parameter. So think P, population, and parameter. And then we talk about S being our sample statistic. Therefore, whenever we're talking about a parameter, remember that is dealing with population. Whenever we're talking about a statistic, that means that we were talking about something from a sample. So a parameter is a number that describes some characteristic of the population. For example, the mean, the median, standard deviation, those are all numbers that describe a characteristic of a population. A statistic is the same thing. It's a number that describes some characteristic of, in this case, it is going to be a sample. So just remember, parameters always describe populations, and statistics always describe samples. And you have seen many of these. We have talked about X bar, which is the sample mean. And we have also talked about mu, which is the population mean. Another example would be S, which is our sample standard deviation. And we have talked about sigma, which is our population standard deviation. Another one that we will start to look at within the next chapter will be p hat, which is a sample proportion. And we've already talked a lot about P, which is a population proportion. How are parameters and statistics related to each other? Well, we use statistics to make inferences about parameters of populations. And we're going to see which ones we can use and which ones we don't have the ability to use.